Welcome to this video. We're going to learn about potential and potential difference. First, imagine we have some space, and in this space there's an electric field. So if you put a charge of 2 coulombs at this location, it gets pushed with 6 newtons of force. So you take it away, and you put a bigger charge there, 3 coulombs. How hard is it pushed? 9 newtons of force. So you put another charge, which is 4 coulombs big, and the force it feels is even bigger, 12 newtons. What's the pattern here? We see that the bigger the charge, 4 coulombs compared to 2, the larger the force, 8 newtons compared to 4. But there's another thing to see. 4 divided by 2 is 2. 6 divided by 3 is the same value, 2. 8 divided by 4 is 2. The force per coulomb is always the same value, which we call the electric field strength. So let's try to understand this a little better. If you zoom in on the picture, here's the 4 coulomb charge, which feels 8 newtons of force. I could take the 4 coulomb charge and break it into chunks, and each chunk is 1 coulomb big. I could also take this 8 newton force and break it into chunks, and say that every 1 coulomb is pulled with 2 newtons. That's the same as what we said before, because the 2 newtons add up to make our original value of 8. This value E, this quantity E, electric field strength, is the force felt per coulomb. This value F is the total force felt by all of the coulombs together. We can do the exact same thing with potential energy. Let's say we put a charge down and it has 16 joules of potential energy. Well, if we break this 4 coulombs into 4 different chunks, each is 1 coulomb big, we could say that every one chunk has 4 joules, because when you add up the 4 plus 4 plus 4 plus 4, the total amount is the same 16 joules. The potential energy per coulomb, the value 4, we call that the potential, or electric potential. The potential energy is the total amount. All 4 coulombs together have 16 joules. But the potential is the amount of energy per coulomb. Let's build on this idea of potential energy. Here's a uniform field. At every location inside the field, the strength is the exact same. So let's take a positive charge and put it here. It's naturally getting pushed to the right. It's being repelled from the positive plate, and it's also being attracted to the right toward the negative plate. So where does it want to go? It naturally wants to go over to here. And if we let the charge move from the left side to the right side, what happens to its potential energy? I'm going to make up a number and say it has 16 joules to start. Well, when this charge goes to where it wants to go, when it just follows its natural path, it loses potential energy. That's no different from what happens when you drop a ball. It loses potential energy. We can take this energy of 16 joules and break it into the 4 different chunks, or the 4 coulombs of charge. Each chunk or coulomb gets 4 joules, making a total of 16. And when the charge gets to over here, it still has 4 coulombs or chunks, but now each chunk has less energy. How much potential energy does each chunk have now? Well, 1 joules, because that's what you add to get to 4. The change in potential energy, we're going from 16 to 4, so we're losing 12. But the change in potential energy per chunk, or per coulomb, well, it's going from 4 to 1, so each coulomb is losing 3. 3 joules are lost per coulomb. This value, delta PE over Q, the change in potential energy per coulomb, is called the potential difference. Delta PE is the total loss, and delta V is the loss per chunk, or per coulomb. But there's an important connection. In order for the charge to lose this potential energy, this electric force must be exerted over a distance. In other words, to lose this potential energy and move this distance, work has to be done by the field, by the Coulomb force. So we're losing potential energy, but is the work positive or is it negative? Well, the angle between the force arrow and the distance or displacement arrow is 0 degrees because they're in the same direction. Cosine of 0 is 1, and that 1 goes away. So the work is going to be positive. Now we said that we're losing potential energy. We're going from 16 joules to 4 overall, making a loss of 12. Yet the work is positive. Do you know how big this value is? It's the exact same. The only difference is they're opposites of each other. One is negative, one is positive. So when we write the equation for potential difference, we can put the numerator not as delta PE, but as negative work done by the field. This is exactly how we define potential difference, in fact. We define it as the work done, that's W, per unit charge, to move a small positive test charge from one location to another. You'll notice that we're being a little careless here. We're not describing negative, and we're not saying it's the work done by the field, but that's okay. This definition is sufficient.